In this video, we will use the properties of regular polygons in the area formulas we derived in the previous video to solve some problems here. In this diagram, this figure is a regular decagon, so 10-sided, and it's inscribed inside of a circle, meaning each of these points are right on the circle. And P is the center of that circle. We're going to find some angle measures in here. So I'd like to find angle KPJ, which corresponds to a central angle in the circle made by these two radii from PJ to PK. How would you do that? Well, I know that the degree measure to go once around a circle is 360. And if I did this, if I thought of this as, if I drew in these 10 other radii that go from P to each of these corners, I'd make myself 10 triangles. And they're all congruent because they're all the same radius. So that means that each of these angles in here are equal in size, and there's 10 of these little pieces going around. So if I just take 360 divided by 10, I'll get what this central angle is, which is not 360, but just 36. In general, this is what you can do to find the measure of a central angle, is take the 360 and divide by how many sides they're going to be. So KPJ is 36 degrees. Let's see, LPJ, or LPK, excuse me. LPK is this angle. This angle looks to be, since I drew in an altitude, or better known as an apothem, from P to L, you can show that these two, it's not that hard to show that these two triangles, these two halves have to be congruent using side, or siding, or hypotenuse leg, or whatever method you'd like to use. The important thing is that since these triangles are congruent, that means that these two angles are, that these two smaller angles are congruent, meaning LP bisects this big angle. Long story short, LPK must be half of the whole thing, and half of 36 is 18. Lastly, we'll look at angle LJP, so L to J to P, that's this angle right here. If I think of this, maybe it's easier to look at if you draw a picture, like a zoomed in picture of this. This is a right angle, this is L, that's P, this is J, and we're looking for this angle here. I know that's 90, and we just showed in the previous one this angle's got to be 18. So with some subtraction, we can figure out what this angle is. It's just 180 minus 90 minus 18, which worked out to be 72 degrees. This sort of reasoning we're going to use to help us find some angles to solve these problems that are upcoming. So, our first regular polygon question here. We are tiling a floor with ceramic regular hexagons and with side lengths of 8 inches. What is the area that the tile will cover? Round our answer to the nearest tenth. Don't have a picture, so always start by drawing a picture. Even if it's a bad picture like mine, step one is always draw a picture. And I'm going to label this picture. I can do better than this. I know that the side length, I know this is a regular hexagon, so all these sides are the same length, and they're all 8 inches. I think the next thing you should, after you've labeled everything you know, is we should decide how you're going to approach finding the area of this. No matter what you do, it should involve finding the area of dividing this into smaller triangles like we talked about in the previous video, finding the area of one of these congruent triangles, and then multiplying by how many there are. I think you should decide which area formula you're going to use. Decide which formula to use. To make that decision, if I were you, I would take I would decide what information I have and decide what's the least amount of effort I need to put in to finish this problem. What's the least number of things I need to calculate in order to figure out what the area of this thing is. In this case, I know what a side length is, and I know that one of the two formulas that we had uses side lengths, which means that I'd only need to, and I can count how many sides there are. There's 6 because it's a hexagon. So I already know the number of sides. I know n. I know what the side length is, s. That means the only thing I would need to calculate is what an apothem length is. So I think because of that, because I know what the side length is, I think in this case I'm going to use the formula that uses side lengths and therefore apothems, which in this case that was the formula that area is 1/2 the apothem length times the side length times the number of sides. An apothem goes from the center to this triangle at a right angle. That's what my apothem is. It's over here. So I'm going to draw a series of pictures to kind of zoom in that are going to help me kind of better understand what's going on in here. If I look at the one triangle I need to find the area of, it might look something like this. I have one triangle, looks something like this. You know, this side is 8, and I'm looking to find what this apothem is. In order to find this height, one way to do that would be, it might be, if I knew what, say, some angles are in here, I could use SOHCAHTOA or trig to do that. And I can quickly find the area of I can find a central angle. A central angle, which would correspond to this angle. Since there are 6 sides, there are 6 of these central angles, and these 6 angles go around and make a full circle. So I think this angle, the central angle, is a full circle divided by how many central angles there are. In this case, there are 6. So I think this whole angle is 60 degrees. Or maybe better yet, maybe a more useful triangle might be if I looked at just half of this triangle, like say the right half. Half of this angle should be 30 degrees. This is still the apothem. And this bottom is, well, I cut this triangle in half with this, so this piece is 4. If I know an angle and I know a side and I'm looking for a missing side, I can use SOHCAHTOA to try to find this missing side. So I think from this 30-degree angles perspective, I know the opposite side and the adjacent leg. Opposite and adjacent is TOA is tangent, so I think the tangent of 30 degrees is equal to 4 over A. Cross multiply, A times tangent 30 is equal to 4. Divide by whatever the tangent of 30 is on both sides. And I find the apothem length is 4 tangents of 30 degrees. I know what A is now. I know what the side length is, that's 8. And I can count the number of sides, that's 6. So this should be, the area of this triangle is 1/2, 4 over tangent of 30. Times the side length of 8 times the number of sides, which is 6. And according to my calculator, that is 0.5 times fraction 4 tangents of 30 times 8 times 6 is 166.277. I'm rounding my answers to the nearest tenth. So this I think is 166.3. And the unit is square inches. Let's try this again. Let's find the area of this regular hexagon, and we'll round our answers to the nearest tenth. Again, here's a hexagon. This time this diameter is 32. So that tells me that I know the radius is better be half of that. My picture's already drawn, so I don't need to worry about that. The triangles I'm looking for look something like this. And I'd like to decide kind of which area formula seems to work is going to be the easiest for me to use in this case. I think the second area formula we saw earlier, which uses the radius and the central angles, is going to be much more efficient than trying to find apothem lengths and side lengths. Because the other area formula is 1/2 times the radius times side, or radius times radius squared, times the sine of the central angle, times the number of sides. And I already know the radius, that's 16. I can count the number of sides, that's 6. And I can actually quickly calculate the central angle, as we saw in the previous problem. So this formula is going to be super easy. 1/2 the radius is 16. The central angle of a hexagon we saw in the previous problem is 60, but if you weren't quite positive, you could just take 360 and divide by how many sides there are. There's 6. 60. And then there are 6 sides. So according to my calculator, 1/2 times 16 squared times the sine of 60 degrees times 6 is 165.108, or to the nearest tenth, this is about 665.1 square units.